All right, so let's look at something that we're going to develop more and more. And what we're going to see here is we're going to see that the standard deviation becomes something that we can measure with. So let me put what's going to be called a normal curve or a Gaussian or a bell curve. I'm going to try to avoid the word normal. It has connotations that we're going to look at as we develop the concepts of what we use standard deviation for. But normal is our perception of things. I think what we're saying is the data that we choose to observe clumps, and clumps in a certain way. And so we want to look at that clumping. So let me try to draw this curve here and see what I can get out of it. So let's see. There we go. Okay, almost. All right, we'll do some smoothing here, but this is a bell-shaped curve. And what happens in general is this curve slopes down, right? It's curved inward. It's a frowny face. And about here, it starts curving upwards, or a smiley face. We say the curvature changes. And these are inflection points. Inflection points are where a curve changes directions. And for the normal curve, these inflection points happen a distance on either side of the mean. So if the mean is in the middle, right, the mean, median, mode are in the middle, then in this inflection point here and this inflection point here cover +1 standard deviation and -1 standard deviation. They're a measurement. And if I draw down here, a certain amount of our data falls in between one standard deviation. And we get 34% here and 34% here on either side of the mean, or a total in this yellow area of 68%. I'm going to extend this down further, and I'll say, and so in between one standard deviation on either side of my mean is 68% of my data. More than half of my data lies within this. We think of this as being filled with data points. Well, if I go a little further out by one more standard deviation, because the standard deviation is becoming the thing we measure with, and so we're measuring in standard deviations, I get 13.5% here and 13.5% here. Or in total, and I went out one more standard deviation, so from the mean to the orange line is +2 standard deviations and -2 standard deviations, or a total of a 4 standard deviation range. We say it's within 2 standard deviations plurally because it's 2 on either side. And within there, within the orange area, includes my original 68%, I have a total of 95% of my data. And if I go out further, let me change color one more time. If I go out further, and I go 3 standard deviations, so +3 standard deviations and -3 standard deviations on either side of the mean, I get in here another 2.35% and another 2.35%. And all said and done, it's 99.7% of my data. And so almost all of my data is within 3 standard deviations. And we're going to find that standard deviations become a way of measuring the position of data, or a way of determining how rare something is. If most of our stuff was within 1 standard deviation, when we work our way further and further past 3 standard deviations, something's very rare. If you're past 2 standard deviations, you're unusual. And so we have this means of measuring how far out an individual piece of data is. And the standard deviation is going to be that tool. And it tells us where most of our data is, where a lot of our data is, and where almost all of our data is. Now, remember this normal, this Gaussian, or this bell curve is symmetric. It has the mean, median, and mode are equal. And in this, the data falls through equally across. And we'll study more in Chapter 5 what this means and how this gets created. But for right now, it's not a bad approximation for a lot of our data. And so we can talk about how rare events are or how many people we could expect to find in certain areas of our data. Now, if our data isn't normal or Gaussian or in the bell curve, we can still get a lower bound of how much of our data is in a certain region. And we do this, using Chebychev's rule. And what Chebyshev said was, hey, if you're not symmetric, but we can say that for values of k greater than 1, that we can find a percentage of the data. And so I'm going to take 1, which is 100%, right? 1 is our way of saying 100% in ratios. 1 over k squared. And this will give us a percentage when k is the number of standard deviations. From the mean on either side. So back up here, when we looked at our normal curve, I said I'm within 1 standard deviations on either side of the mean, and I found 68% of my data. Here I said I was 2 standard deviations on either side of the mean, and I had 95% of my data. And these percentages hold for this type of distribution, this Gaussian, this normal, this bell curve. If I don't have a Gaussian or a bell curve, I can use Chebychev's rule to know how much, and this percentage is at least this much percentage. It's not as telling as the standard curve, which gives me how much is in between things. This is at least so much lies within. So for example, within 2 standard deviations, k is equal to 2, and 1 minus 1 over 2 squared is 1 minus 1/4, or 3/4, which is 75%. So let's look at a distribution that isn't balanced, isn't symmetric, and we'll say we surveyed people and we looked at how many television sets they owned. 2, 3, whoops, that should be a 3 down there, so 1, 2, and 3, 4, 5, 6, and we find that the average number of television sets is 3 with a standard deviation of 1. And so we want to know how many people have between 1 and 5. And so 1 and 5 is here. We want to know at least how many people, let me change color for that. Want to know how many people are within this bit of our distribution. At least. Now this is not symmetric. This is not a normal curve, so we'll use Chebyshev's formula, which is the 1 minus 1 over k squared is the percentage. And so our mean is at 3, and our upper bound 5, and our standard deviation is 1. So if I go out 1 standard deviation, that takes me to 4. If I go out 2 standard deviations, that takes me to 5. Go on the other side, down 1 standard deviation, that takes me to 2. I'm going to go down 2 standard deviations, that's taking me to 1. So on either side of the mean, I have 2 standard deviations plus and 2 standard deviations minus. And so Chebyshev would say, hey, I have at least 1 minus 1 over 2 squared, or 3/4, or 75% of my data is within this bit, at least. In fact, looking at this plot, there's more than 75% there. But Chebychev's theorem is used when things are not symmetric, and so the best we can say is at least.